Hello everyone. So today I will start reaction mechanism. Now, in this we will study how reactions takes place in general. So let us consider a general organic reaction. In this, first we talk about elementary reaction. So what is elementary reaction? One step reaction. Any reaction which takes place in only single step, that reaction is called elementary reaction. In this reaction, no intermediate form. There will be no intermediate form. And see, you know that in every organic reaction, bond formation and bond breaking takes place. So here also bond formation and bond breaking will take place. But in this case, bond formation and bond breaking will take place simultaneously in a single step. And that step is called transition step in this case. So in this case, bond breaking and bond formation takes place simultaneously. Bond formation and bond breaking takes place simultaneously. Now in this A plus B is getting transition into C plus D, that is product. There will be one transition step. Now here we will see this is multi-step reaction, or it is also called complex reaction. So here we see first this A is converting into intermediate, then it is converting into product. So in this case, either in first step bond breaking has taken place, and in the second step bond formation has taken place. So first this A is converting into intermediate, then this intermediate is converting into product. So in this case, two step is involved in the reaction. So that is called two-step reaction. So it is two-step reaction. Now how many transition steps will you form in this case? See, A is transition into intermediate. So whenever there is some transition, there will be a transition step, either by bond breaking or bond formation. So here this A is getting transition into intermediate. So there will be one transition step here. Now this intermediate is getting transition into product. So this intermediate is getting converted into product. So there will be one more transition step here. So in this case, two transition steps involved. Here there is no intermediate. Here there is one intermediate, and here in this elementary reaction there is only one transition step, and in the two-step reaction there will be two transition steps. So in this case also bond breaking and bond formation will be involved. Either in the first case there will be bond breaking or bond formation. Bond breaking and bond formation involved. Second, see in this case transition state and intermediate both are involved. Transition state and intermediate both are involved. Now see the third case. So in this case there are two intermediates are forming, and it's a three-step reaction. First this R is converted into intermediate, then this intermediate is converted into intermediate 2, then this intermediate 2 is converted into product. So this is three-step reaction. Now whenever there is a transition, whenever there is an arrow sign, there will be one transition state involved. So in this case there will be three transition states: transition state 1, transition state 2, transition state 3. Now we'll see the energy profile diagram for this reaction. So if we draw the energy profile diagram for this elementary reaction, here is potential energy on y-axis, and on x-axis it is progress of reaction. So you know every reactant or product have some energy. So initially we have taken these reactants, they have some energy, so they will have some energy. Now how the reaction takes place? So you will study in thermodynamics. Reaction only takes place when two molecules collide with each other. So when they collide, their energy increases, and only those molecules convert into product whose energy increases by a certain amount, and they collide at a certain energy. So when they will collide, their energy will increase, and then again they will start converting to product. So when they will start converting to product, their energy will decrease. So at the highest energy, transition state will form, and it's also called activated complex. So in this case, there is only one transition state form, so there is only one maxima. So if number of maxima in energy profile diagram, that number of transition state will form, or you can say number of maxima. So in this case, number of maxima is 1, so there is only one transition state. Transition state will be equal to number of maxima in energy profile diagram. Now if you draw the energy profile diagram for this reaction, so potential energy. Now in this case also, reactant have some energy, then they will collide with each other and energy will increase. Then it is forming intermediate. Now this is intermediate, and intermediate will have always more energy. It will be unstable than reactant and product. So intermediate will have more energy than both reactant and product. Now this will again go into transition, and again it will convert into product. So this is reactant. This is reactant A, this is product B, and this is intermediate. Now this is transition state 1 and this is transition state 2. Now this can be greater than or less than transition state 1. It depends on the reaction. It's not here I have drawn it's less than transition state 1. Energy of transition state 2 is less than transition state 1, but it can be greater than or less than. It depends on the reaction. Now you will have to draw the energy profile diagram for this reaction. Pause the video and draw the energy profile diagram for this reaction. I am drawing now only, but you have to pause the video and draw by yourself. This is potential energy. This is progress of reaction. So in this case, reactant will have some energy, then two intermediates will form, and second intermediate will have less energy than first intermediate. This is reactant R, this is intermediate 1, this is intermediate 2, this is product. Now in all these three reactions, I have assumed that product is more stable than reactant. That's why reaction is proceeding in forward direction. So this is transition state 1, this is transition state 2, this is transition state 3. So transition state energy can be greater or lesser than each other. It depends on the reaction. Now you see the energy. Now we'll see the types of reaction based on the energy, based on the free energy. You know this. You have already studied types of reaction based on the free energy. The types of reaction on the energy, based on the energy. Types of reaction based on free energy. Free energy nothing but energy only. Types of reaction based on free energy. So I'll draw two diagrams. One is this, and another one is this. So this is one type of reaction, this is another type of reaction. Now tell me what type of reaction is this? This is exothermic reaction. This is reactant and this is product. Here this is reactant and this is product. So this is exothermic reaction and this is endothermic reaction. Now in the case of exothermic reaction, delta H is less than 0. In the case of endothermic reaction, delta H is greater than 0. Now you know all this, you know already these reactions. Now we'll see Hammond's postulate. See, in the case of organic reaction, I have assumed that product is more stable than reactant. Now we'll see Hammond's postulate. Why is Hammond postulate? See, Hammond is a scientist. He gives postulate about transition state. Here, for this reaction, this is a transition state. For this reaction, this is a transition state. Now, he said that according to Hammond's postulate, transition state resembles more to the structure reactant or product. Transition state resembles more to the structure reactant or product which is closer to the energy of transition state. So it means, like, according to Hammond's postulate, transition state will have more properties of between reactant and product, which is more closer to the transition state. So if you see in the case of exothermic reaction, transition state is more closer to reactant. So transition state will have more properties of reactant than product. It will resemble more properties of reactant than product. If you see in the case of endothermic reaction, the product is more closer to transition state. So transition state will be resemble more properties of product in compared to reactant. So you can write in exothermic reaction, transition state resemble more properties of reactant. Because they are potentially closer. It means potential energy difference between them is less because they are potentially closer. Now, in the case of endothermic reaction, transition state resemble more properties of product, because they are potentially closer. Potentially means that their potential energy difference is less. Potentially closer. See, in this case, transition state is more closer to reactant, so it will resemble more properties of reactant in the case of exothermic reaction. In the case of endothermic reaction, product is more closer to transition state, so it will resemble more properties of product. That is Hammond's postulate. So transition state will resemble the more properties of that reactant or product which is more closer to its energy in the energy profile diagram. Very important Hammond question. Now next, we'll see attacking reagent. Attacking reagent. So suppose in a reaction a reactant is present. Now on this reactant a reagent came and see it will attack on this reactant and product will form. So how this reagent will attack on this reactant? So in the organic reaction either it will take the electrons from this reagent or it can give the electron to this reagent. So either it can take the electron, it will attack in two ways. This attacking reagent will attack this reactant in two ways. Either it will take the electron, or it will give the electron. So either it will give the electron to the reactant or it will take electron. So it in two ways it can attack the reagent and attack the reactant and product will form. So there are two types of attacking reagent. There are two types of attacking reagent. It's called electrophile. First is electrophile and second is nucleophile. Electrophile is also called electrophilic reagent. Electrophile or electrophilic reagent. Second, nucleophile or nucleophilic reagent. First we'll study of electrophile. So electrophile is made of two words, electron and phile. Electron plus phile. So electron means electron and phile means loving. So electron loving. The reagents which seek electrons or the electron loving reagents. All reagents which seek electrons are called electrophile. So first definition of electrophile is all reagents which seeking electrons are called electrophiles. Or you can say there is one more definition. All reagents which are electron deficient, they also need electrons, they will seek electrons. All reagents which are electron deficient are called electrophile. They have deficiency of electron. Now, there will be any other type of electron. So reagents having vacant orbital. Reagents having vacant orbitals, they also need electrons to complete their orbitals. Vacant orbitals, or they can seek electrons, like especially P or T are also electrophile. Or there will be one more case when during the reaction, when any compound will become electrophile. So maybe vacant orbital during interaction. reagents having vacant orbital or maybe vacant orbital during interaction. Maybe vacant orbital during interaction. So this last one, or maybe vacant orbital during interaction. See, in this case, what will happen now? Some of the reagents will have vacant orbital during the reaction. During the reaction, they will have vacant orbital. So they will also count as an electrophile. So next we'll see the types of electrophile. So first is incomplete octet positively charged electrophile. Incomplete octet positively charged electrophile. So it will be H plus, D plus, T plus, CS3 plus, CS3 plus, Cl plus, Pr plus, I plus, etc. They have incomplete octet and they are positively charged. Second is incomplete octet neutral electrophile. See, in this case, they will be neutral and they will have incomplete octet. So it will have BF3, BCl3, BVR3, or you can say AlCl3, or D block metals. D block metals compound like FeCl3. Fe has empty vacant d orbital, so it can take electrons. Or you can say HbCl5, etc. They are neutral, but they have incomplete octet. In this case, you can also write NO2 plus, NO plus, etc. Now, C, this is the important. Complete octet. Complete octet electrophile. They have complete octet, but still they will act as a electrophile. This is this section. Maybe vacant orbital during interaction. So if you take example CO2. Now you see this all have complete octet, but still this is a electrophile. Why? See, oxygen is very electronegative than carbon. So delta negative charge will come on oxygen, delta positive charge will come on carbon. So if any nucleophile will come, this bond will goes to the oxygen and carbon will become vacant. Carbon will have vacant orbital. So the nucleophile will attack on the carbon due to delta positive charge. So this CO2 will also act as an electrophile. So whenever CO bond will be present, that will act as an electrophile. Similarly, if we take SO3, SO3 will also act as an electrophile because delta positive charge will come. So any nucleophile will come, it will become backend. So maybe backend orbital during interaction. So they will become backend orbital during interaction. So they will also act as an electrophile or ketone. If C double bond O bond is there, so then they will act as electrophile only. Aldehyde, ester, acid, anhydride, acid halide, amide. Wherever C double bond O bond is there, they will act as an electrophile. Another type of electrophile is interhalogens compound. You know, interhalogens compound. ICl, IBr, IN3, ClOH. They all have complete octet, but they are also act as a electrophile. Here one I delta positive charge. This site will act as electrophile. In CO2, carbon will act as electrophile. In IBr, this I will act as electrophile. In IN3, this I delta positive charge will be on I, so I will act as electrophile. In ClOH, this Cl will act as electrophile. Delta positive charge will come on Cl because Cl is connected with oxygen. So delta positive charge will come on oxygen. See, in all these cases, polarization of pi electron is taking place. This pi electron is moving on the oxygen. In this case, polarization of sigma electron is taking place in ICl, IBr, IN3 and ClOH. So there are one more type of electrophile, that is NOCl. No, NOCl, okay, CNOCl. So this is very, very important. This is called Tilden's reagent. This is called Tilden's reagent, NOCl. Now tell me on which positive will come, which will act as an electrophile in this case, NO or Cl. So if you draw the structure of this reagent, it is like this: N double bond O Cl. This is the structure of this reagent. Now this will break from here and will convert it to NO plus and Cl minus. So delta positive charge is coming on the nitrogen and negative charge will come on chlorine. So NO plus will act as this part will act as electrophile in this case. This NO plus is electrophile. So this is very important. This NOCl is a electrophile and in this case NO plus will act as a electrophile. Now there is a compound A, there is a reactant A, and here some electron rich compound is there. Now whenever electron rich compound is there, so if this is A, so if electron rich compound will be there, just like a strong acid and weak acid, so it is electron rich, this will start behaving as a electrophile. So this type of electrophile will be like this: Cl2, I2, Cl2, Br2 and I2. So in whole organic chemistry, this Cl2, Br2 and I2, they act as an electrophile only. They only react whenever electron rich compound will be there. So they will always act as an electrophile in organic chemistry: Cl2, Br2 and I2. Now tell me, between A, B and C, what is the order of electrophilicity? Which is more tendency to take electron. So between A, B and C, order of electrophilicity will be A, B and C. Positive charge is there, so they will need more electrons. So they have more electrophilic character. So then A, B and C. This is the order of electrophilicity. Next is nucleophile or nucleophilic reagent. Second is nucleophile or nucleophilic reagent. So nucleophile means nucleus loving. Now whatever compounds will act as a nucleophile, those having an electron density, those having a dense electron density. So having dense electron density or high electron density, having high electron density, if they have high electron density, they will act as a nucleophile. So what are compounds? So if they have high electron density, nucleophile can donate electrons. So what type of compounds can donate electrons? Compounds having lone pair. Lone pair, if they have lone pair, they have high electron density and they can donate their lone pair, or pi bond. Bond pair also. In the case of bond pair, pi bond are loosely bound, so they can also donate their pi bond. So if there is pi bond present, so they can also act as a nucleophile. Pi bond pair electron. Now you see the types of nucleophile. In types of nucleophile, first we see the negatively charged nucleophile. So in negatively charged nucleophile, like it will be OH minus or like H minus, D minus, T minus, F minus, Cl minus, Br minus, I minus, OH minus, SH minus, NH2 minus, RO minus, RS minus, all will act as a PTC. They all are nucleophile. Negatively charged nucleophile. Second, neutral. Neutral nucleophile. So in this case, example will be ROH, alcohol. This is lone pair. So it can give its lone pair. So it will act as a neutral nucleophile. Second, you can see H2O, H2S, thiol, 1 degree amine, 2 degree amine. They have lone pair, so they will also act as a nucleophile. 1 degree amine, 2 degree amine, ammonia, NH3, etc. So these are neutral nucleophile having lone pair. And see, this is the part A of neutral nucleophile. Now I will say those compounds also can act as nucleophile, which is pi bond pair electron. So we'll see the example. See this CS double bond, CS2 double bond, CS2. Now this will also can act as a nucleophile. CS3, CS double bond, CS2. Now tell me, between these two, which is more nucleophilicity, which is more electron density? So in this case, we see because of this CS3 group, this has more electron density. This carbon has more electron density because this CS3 has plus H effect. So these two compounds are also act as a nucleophile. and this one has more nucleophilicity than first one. Similarly, benzene has 6 pi electron density, so benzene will also act as a nucleophile. We have alcohol will also act as a phenol will also act as a nucleophile. Similarly, amine, aniline will also act as a nucleophile. These are, in this case, pi bond electron will be involved in nucleophilicity, having pi bond pair electron. Third type of nucleophile will be positively charged nucleophile. This is very rare. Positively charged nucleophile. See, this is what NH2. Now, if we add one more H, it will become NH3. This will become NH3 plus, and this will become NH2. Now, if you see, they are not in resonance. This lone pair is not in resonance with this positive charge, because this is also sp3 and this is also sp3. Lone pair only involved in resonance when there will be sp2 hybridized group at S position. So this lone pair is not involved in resonance. So this lone pair will give its electron to some other. So that's why this whole compound will act as a nucleophile. So positive charge of nucleophile also possible, and this is the one case. Another will be, here I will like OH and NH3 plus. It's not that important, but positive charge nucleophile can also possible. In this case, this NH3 plus is positively charged. Now this plus charge here is formal charge, because nitrogen can form only 3 bonds. The fourth bond is coordinate bonds. This is not an actual charge. This charge is formal charge in this case. Now fourth one, no, only these 3 cases. Now write some important point. First is Na plus, K plus, Li plus, Na plus, K plus, Rb plus. These are not electrophiles. Are not electrophiles. See, alkali metals cations are not electrophiles. Second, Ag2 plus or Ag2 plus. D block metals cation can act as electrophile. So here Ag2 plus and Ag2 plus are electrophiles. And third point is H3O plus and NH4 plus are weak electrophile. See, don't see if they are positive charge, they will act as a strong electrophile. They are weak electrophile because this positive charge is a formal charge. If you see, H2O can form 2 bonds. Oxygen can form 2 bonds. One H plus is coming, it is converting into H3 plus, H3O plus, and positive charge coming on oxygen, because oxygen is giving its electron to hydrogen. It is forming coordinate bond. So this positive charge is formal charge. Whenever a atom is forming more bond than its actual bond, if charge is coming on that atom, that charge is formal charge. So here this charge is formal charge. Now what is happening? On this oxygen, formal charge is there. So this oxygen is pulling the electrons present between this oxygen hydrogen bond. Now, but it will not able to pull completely. So whenever any nucleophile will be there, whenever any nucleophile will be there, just like here we take NH3. So what will happen? Because this oxygen is pulling the electron present between this oxygen and hydrogen bond, there will be some positive charge on this hydrogen. So this nitrogen, lone pair present on nitrogen, will attract this hydrogen, and then oxygen will take its electron, will be able to pull the electrons. So in this way, it will act as a electrophile. So it is a weak electrophile. It is not a strong electrophile. Similarly, fourth one, BH4 minus. BH4 minus will act as a weak nucleophile. Will act as a weak nucleophile. Same reason as above. This charge on the BH4 is formal charge because boron can only form 3 bonds. So if it is forming 4 bonds, it means this charge is formal charge. So it will not as a weak, act as a strong nucleophile because of negative charge, because this charge is formal charge. So it will act as a weak nucleophile. So that's it for today. Thank you.